Hey guys, it's Jill here. Welcome back to Intermediate C++ tutorial 24. Today we're talking about maps. And I'm not talking about that thing that you use so that you can avoid asking people for directions at all costs. No, I'm talking about std map. And, well, what's it for? What does it do? Oftentimes beginners will ask me, how can I switch on a string? I've got maybe users entered a command. I've got a bunch of different responses or actions I want to take. I want to switch on a string. And the fact is you can't do that. Switch only works on integral types. But we can get the same kind of behavior by looking strings up in a map. The basic use of a map is pretty straightforward. You include map, and then you create a map container, and you have to template it on two parameters, not just one. The parameter of the lookup type or the key type, and the parameter of the value type. So you're going to use keys in order to look up values in your map. That's how it works. So to do this, first you have to insert some key value pairs into your map. So here I'm just doing map insert, and I'll go into the details of this a little bit later, but I'm inserting 3 pairs, and then I get a command from the input, and I look up the response to that command in the map. And the lookup is the same as indexing into an array. You give the key type, and it will return a reference to the value type. So if I type into here, press enter, I get the response that I had set up in my map. Now, you could make this container yourself, and you might make it by just have a vector of structures that have key value pairs. And then when someone tries to look up a key, all you do is you run through your vector and you check every single element. That's a linear operation. It's going to be on the order of n, meaning if you have 1,000,000 elements, then your worst case is going to be, it's going to take 1,000,000 comparisons. And your average case is going to be about 500,000. Now, the beauty of map is it does it much, much faster. It does it in log n time, which means worst case is going to be about 20 comparisons. So what would you rather have? Would you rather have an operation that takes on the order of 1,000,000 for 1,000,000 elements, or one that takes on the order of 19 or 20 for 1,000,000 elements? I know which one I would like. Now, the question you might be wondering is, how does map achieve this magical greatness? And the way it does is it uses a data structure called a tree, binary tree. And so what I'm going to do here is I'm just going to go over the data structure because I think it's interesting, and I think it's also important to learn the basic data structures of computer science. Now, this web page is one of the main things I want to introduce to you. It has animated visualizations for a lot of common algorithms and data structures. So I highly recommend this. I'll try to put a link to it on the wiki if I remember, but you can just see the address right here. We want to look at binary search trees. So the way it works, well, let's insert a few values into our tree. So we'll insert 50. There we go. Works with the enter button. That's nice. Let's insert 35. And it is going to put it here. Okay, so we can see right now, this is kind of like a linked data structure, like a linked list. But it's a little different than a normal linked list because you can see here, if I try to insert 75, this element here, this entry or whatever you want to call it, it has 2 links. That's why we call it a binary search tree. So unlike a linked list where every element only has 1 link and it's just a chain, this one has 2 links for every element, so it can form a tree, a binary tree. And if we keep inserting elements, I think you can guess where they're going to go. So let's try to insert 37. Now this one is full. This 50 is full. So 37 is less than 50, so it's going to check on the left-hand side. Because the less values go on the left-hand side, the greater values go on the right-hand side. So it checks this one, 35, and then 35 is less than 37, so it's going to put it here. Let's test our theory. Check that one, put it to the right. And again, if we do an 80, it's going to check this one, put it to the right. And then if we do, let's say, a 76, it is going to check this one, it's less than, put it on here. And there you go. Let's put a 73 in there. check this one, check this one's less than, put it there. And that is how the binary search tree is built. And because of this binary search structure, what you can do is, well, let's flesh it out a little bit more here. We're going to put so now when you want to retrieve something from this list, it is going to be, or from this tree, it's going to be very fast, because every time you check, you start at the root node, every time you check, let's say I want to retrieve 31. So I'm going to check here, is 31 less than or greater to 50, or is it equal to 50? And we say it's less than. So right now, I know I can remove this whole half of the tree from my search targets. So every time you make a comparison, you're basically cutting the amount of work you have to do in half. And that is where you get the log2 behavior. So I check this one, then let's do it. Now it's going to turn the speed down a little bit. And let's put in here, what did I say? 31? So let's put 31 and we'll find it. So we look here, it is less than. We look here, it is less than, and we have found it. There you go. Now, deletion of nodes from a binary tree is a little more complicated. I'm not going to go into super detail about how it works. You can look that up yourself. But just to have a little demonstration, we can try to delete 65 here. And what you're going to see is first it's going to try to find it, and once it's found it, it's going to delete it, and it's going to try to find a replacement. So it finds a node that is going to be between 63 and 80 down the left-hand side of the tree, and then it puts that node up into here. It goes down into the children. But we can see it doesn't always go to the leaf node children. Sometimes it will pick a closer one. Like in this case here, if I try to delete 64, not 63, 64, what it's going to do is it's going to go down the lesser side, and it is going to find 63 and promote that one up to here. And there you go. So there's a few things going on. Deletion is a little trickier. If you're interested, you can look that up yourself. Of course, the beauty of using std map is we don't have to know anything about binary tree structures or algorithms. It just works. In fact, map is not specified as using a binary tree, and in reality it doesn't use the kind of binary tree that I showed you. It uses a more sophisticated one, but the basic concept is the same. So yeah, you don't have to understand binary trees to use map, but it's nice to know a little bit about how that shit works under the hood. All right, let's take a little more in-depth look at std map. Here's the documentation. As we can see here is a template class. The first two template parameters are the key type and the value type. The key type doesn't have to be a string, obviously. It can be an int, it can be some custom type. The value type can likewise be pretty much anything that you want. And maps, they are containers that contain pairs of these key and value types. Now, create a map like this, pretty straightforward. Inserting into maps, so what's going on here? Well, what you're actually doing is you're inserting a pair. There's a type, it is called std pair, and it is a template type, and the templates parameters are the first member and the second member. So here we got a std pair of string and string. So the first member is a string, the second member is a string. And this just gives you a structure with a couple of public data members and some usefully defined operations and stuff like that. And this is what map uses as its elements. So you construct a pair, and then you pass it to map, and it'll insert that pair into the binary search tree. But obviously this is annoying to type out every time, and C++ can deduce that we want to create a pair. So all we have to do is give it curly braces, and it will create that for us. Now there is another way, an even better way to insert stuff into our map, and it is called map in place. And what this one does is it will construct the pair in place. So all we do is we give it the parameters for constructing the pair. We give it the key and the value type, and it will construct that pair for us and insert it into the map. Beautiful. And then for lookup, you can obviously look it up with these square braces like this. You give it a key value, and it will return a reference to the corresponding value. Now, You might wonder what happens if you try to look up something that doesn't exist in the map. Do you get an error? Do you corrupt memory or something? Well, let's try something. Let's go QQQ. We look that up and nothing. It's just a blank space here. So what actually happens is if you try to access an element that doesn't exist, it will create a new element in the map. So if the key doesn't exist, it will create a new element that contains that key and a default constructed value. In our case, a default constructed string, which is just an empty string. So accessing something that doesn't exist will make it exist. So this really can never fail. If it exists, it'll return a reference to the existing one. If it doesn't exist, it'll insert. Now you might wonder what happens if you try to insert with a key that already exists in the map. And that's a good question. If we take a look at insert or in place, doesn't really matter which one, let's look at in place. We see that it returns a std pair, but this is not the same std pair as is used for the elements of the container. This std pair returns an iterator in the container, and it returns a bool. And the bool signals whether or not an insertion took place. So if you try to insert with a key that already exists, it will not do the insertion. It will not overwrite the existing thing in there, but it will instead return a bool saying false, and it will return an iterator pointing to the already existing element. And if the insertion was successful, it'll return true in here, and it'll have an iterator into the newly inserted element. So that's very useful, because you might say, why don't we just use the square braces for inserting and for retrieving? And the answer is, if you use the square braces for inserting, you might accidentally overwrite something that was already in there, and you might not want to overwrite it. So using insert and in place gives you more control. You can determine maybe you don't want to overwrite it if it already exists. You can do the check to see if it exists and the insertion all in one operation. Similarly, for lookup, you might not want to look up if you're not sure if the key exists, because like I said before, if you do a lookup and it didn't exist, it's going to insert a new element into your map, a new empty element. You might not want to insert, you might just want to check to see if something exists. So what you can do is you can do map, let's see, you can do map count, and that will give you, it'll return 1 if that key already exists in the map. You can't have duplicate keys in a map, by the way. Or you can also do map.find, and you give it a key value, and let's find so, and it will return an iterator to the element. And then you can do, now remember, elements, they contain key and value. So first is the key, second is the value. Then you can get the value of that if you wanted. So if I go std cout map, I don't want wcout, do I? Map.find, that'll give us the iterator, and then we want the second member of the iterator, which will give us the value. And if we run this, it should output, yeah, it outputs the value that was mapped to so. Now, like any container, the map has iterator functions begin and end. You can get iterators and iterate through all the elements. You don't have to look them up. You don't have to know their keys. You can just iterate through all the elements and do something on every one of them. And another interesting thing about map is it is a sorted container. Because of this relationship here with the left and the right nodes, when you iterate, it will iterate over them in order. So here I'm iterating over all the elements in the map, and then I'm printing out for each element. I'm printing out the key value and the value. I gotta stop calling it key value, that's confusing. But we run that, and we should get everything that is in our mother truckin' map. That's the first thing we printed out just from there, and then we got the this one, Cash Me Outside, Crab Dance, and so. And you see they're alphabetically sorted in order of their key. Now this brings me to another important topic about maps, and that is the requirements on the key type. Key type has one major requirement, and the requirement is that it has to be comparable with other keys. How you determine that is the template for the map class The third parameter is a functor for comparison. This is the function used to compare keys to each other, and it defaults to std less. So by default, keys have to implement the less than comparison. And of course, strings and ints compare that, or they implement that, so that's no problem. But if you have your own custom type, you're going to have to implement either less than, or you're going to have to provide your own comparison operator. And I've done this before for creating maps, for example, 2D coordinates. And I used a map to map 2D coordinates to some other kind of data type. So I had to provide a comparison to compare basically vec2s to each other. Now, the last major operation you're going to want to do on your maps is you're going to want to be able to erase elements from them. And just like with vector, mainly you do that by giving it an iterator, and it will erase the element at that position. You can also give it a range with iterators. It'll erase multiple elements. Another very useful overload here is you can erase by key. So you can give it a key, and it will erase the element that has that key if it exists. And it returns a number here, basically an integer number of elements erased. It's going to either be 0 or 1. So that's std map erase. Now, there is one little tricky thing that you have to know about associative containers, like std map and removing elements. So a very useful algorithm that we want and that we use a lot is remove if, right? Std remove if. So here's a standard remove if invocation. We're going to call it on the map. And what we want to do is basically just remove all the elements whose keys are, the string is longer than 2 characters. And that seems reasonable, except it won't compile. And basically the reason why, well, it's complicated, but remove if does not work with associative containers. Not yet. It might in the future, but right now you can't use it with them. So the question then is, how do you remove a bunch of elements from a container, an associative container like map? The way you do it is, well, you would go for I is equal to map begin, as long as I is not equal to map and I++, so we're just iterating over all of them. Now here's the tricky thing. You want to erase, so you want to do your predicate here. So if I pointer to first dot size is greater than 2, we want to erase I. But if we erase I, we're going to invalidate the iterator and we're going to fuck our loop over. So what we want to do is we want to erase returns an iterator to the next thing in the iteration order. So what we can do here is we can go I is equal to I. No, we don't want to do I is equal to map dot erase I. And that will keep the iteration going. Let's get rid of this. It's a distraction. Get rid of that. We'll run it. And here we see we're printing out 2 of them. So we were supposed to erase all of them, but cache me has somehow snuck through. And that's just an annoying little quirk here, because we're advancing the iterator here when we erase, and then we advance it again, we're going to skip one, and that might not be good. So what we want to do instead is we only want to advance the iterator if we do not do an erasure. So what we can do there is we put the iterator advancement inside the body of the loop, and if we run this, now it works properly. It only the only one remaining is the one that was supposed to remain. But yeah, so you can't use std remove if yet with associative containers. That's one downside. Now, the other thing that you have to know about associative containers, and this is very, very important, is that you are not allowed to modify the keys. So if I go first and I try to modify this key to 69, is going to say, no, that's bullshit. Because, I mean, think about it. The keys determine the structure, or the structure of the binary tree. And if you modify one of the keys, you have now invalidated the structure of the binary tree. It is no longer valid. It will no longer give proper results for searches, etc. So once you insert an element, the key is basically written in stone. If you want to change the key, you have to remove the element and reinsert it with the new key. Those are the 2 main things you should know about associative containers. And that's it. That's the major useful operations for std map. Now, associative containers, I've been talking about them for a while here. There are other ones besides map. Map is the, I would say, the most basic one. Now, in the associative containers pantheon, we have map, but there's also set, and then there's multi-map and multi-set. So, what are these guys? Well, set is very easy to understand. Map, you have a value, or you have a key, and it maps to a value. With a set, you only have keys. So a set only has keys, and you can insert keys, and you can check to see if keys exist in the set. But they don't map to any other value. And you might be wondering why I would ever want to do that. Let me give you a simple example of how you could use set, what it could be useful for. So let's say you're given an input sequence, and your job is to output only unique values from that sequence. So if there's a duplicate, you shouldn't output it. So what you can do is you can give yourself a set, and you can iterate through all the input sequences, and you can insert into the set. And if it already exists in the set, that means you've already seen it once, and you can skip outputting that. And then if you do this, you'll only output unique values. So if we run that, so here you go, out of this sequence, we've only outputted here the unique values of the sequence. Now, you might be saying, Chili, you can probably just use an algorithm from the standard library to remove the duplicates. And yes, of course, but it's just an example. There are more complicated uses of set. And I'm just saying here, it can sometimes be useful. If you don't need a full map, if you're not mapping those keys to any kind of values, then you can just use a set, and that's simple. Now, the other category is the multi-associative containers, multi-set and multi-map. And you can probably guess what they do, but map is unique. There's only one key. You can't have two keys that have the same value that compare to equal. But with multi-set and multi-map, you can insert multiple elements with different keys, and they'll all just coexist in the container. And that's interesting. Because then if you want to look something up and there could be multiple of them, what you can do is you can you call equal range, and that returns a range, basically a pair of iterators to the beginning and end of the range, where all of the elements have that key. So you can find, with equal range, you can find all the elements equal to some kind of key. And also here, count is a little more meaningful because it will return the number of elements matching a key, whereas in map, it's always going to be 0 or 1. All right, let's take a quick practical look at multi-map here. So we'll see how this works. We're also going to do it with a custom data type, va2, so we can see how to implement a comparison functor for that. So we obviously, we're going to create a multi-map. va2 does not implement the less than operator, so the default functor will not work. So we got to provide our own functor. So do it like this. The way I'm going to do it is there's no real natural ordering of vectors. What we're going to do is we're going to order first by x, then by y. So the first thing we do is we check to see if the x's are equal. If the x's are equal, we return the comparison of the y's. If the x's are not equal, we return the comparison of the x's. And there you go, you've got your comparator. You create your multi-map with the key type, the value type, and the comparison functor type. And then you just insert some stuff in here. Now, this is a multi-map. We want to test the functionality of inserting multiple elements that have the same key. So we do that here. All these lines have the same key, slightly different values. And then we want to test a lookup of a key that has multiple elements. So we do equal range. Now, equal range returns a pair. This is different than the pair of elements. This is different than the pair for in place or insert. This pair is, the element first gives us the begin iterator, and element second gives us the end iterator. So we get the range, and then we want to iterate over that range. So we get iterators equal to first as long as I is not equal to second. of our range, I++. This will go over the entire range. Note that you cannot use a range-based for loop in here because range-based for loop requires something with a begin and an end function. And this is just a dumb pair. So unfortunately can't do range-based for, but we will be able to do that in the future when the ranges library comes out, I think in C++ 20. But anyways, so we're now iterating over that, and our iterator points to elements, which are also pairs. It gets confusing. There's a lot of pairs. It gets confusing to keep it straight in your head. But this pair is for an element. So the first member of this pair is going to be the key, which we don't care about. We already know that. We're looking for values, and that's the second. So we print out the values for each of the elements in the range. And if we run this, there you go. We get our 3 values that correspond to that key. And that is multi-map in a nutshell. One thing you should note about multi-map is that it has no index operator, unlike map. So you have to use, basically you should be, when you're doing a lookup, you should be using equal range. You can also use find, but the problem with find is if there are several elements with a corresponding key, any of them may be returned. So you don't know which one you're going to get, which isn't that great. So in general, if you're using a multi-map, you're expecting possibly multiple elements corresponding to a single key, and you should be using equal range to get the range of all those elements. But there you go. Those are the ordered associative containers. Very useful, very nice. Obviously looking stuff up based on string is important for a lot of different applications, for command line interpretation or for maybe writing your own scripting language. There's a whole bunch of different applications of that stuff. In a future video, I'm going to show you how not just to map a string to another string, but how to map a string to another function, and so you can actually implement a kind of switch statement executing code based on some kind of string that's input. But that's for a future video. In the next video, what I'm going to do is I'm going to introduce you guys to the unordered associative containers. These guys, they have, it's similar interface to map. A lot of it works the same, but these guys actually run on a hash table under the hood, and that means that they have a little different way of working in the interface, and they also have different performance. Hash data structures generally work on order of constant time, so the time that take to look up does not increase very much even with large data sizes. So 1 million elements, 1 billion elements in the container, and you can still have very fast lookup. So instead of log n complexity, you're getting big O of 1. Very nice. But there's a little bit more complication that goes along with working with a hash container. There's more requirements, and I'm going to get into that, and I'm going to show you guys the basics of how a hash data structure works in the next video. Until then, I hope you liked this video. If you did, please click the like button. It helps a lot, and I will see you soon with some more C++.